Good evening, and welcome back to this evening session. We thought that it would be good for the school to have a corporate perspective on the kind of science that we are doing, and I am very glad and grateful that Dr. Sadasivan Shankar from the Intel Corporation agreed to give us an overview of the top 10 task challenges for enabling computational materials design in nanotechnology perspective. Sadasivan, thank you for being with us.
Thank you. Can you hear me? Okay. So thanks, Stefano, and thanks to Nicola and others for inviting me to give this talk. I actually am also a student of the school at the same time, also giving you a perspective of how we use it. The intent of this is to look at fresher perspectives which come from theoretical side, but we are actually very successful in using some of these techniques which I intend to show today. The point of having the talk title this way is to show that there are more challenges, which explains why I'm also a student, in the sense that you need to find ways of addressing these challenges, because this is what would enable you to have a computational type materials design for the real industry. And thanks to Stefano and Nicola and Julia for getting me involved in this as well. And I would like to acknowledge others who have contributed to this. So this is a sum total of quite a bit of work that we have been doing for the past 7 years. This is a summary of 6 to 7 years of work at Intel. So I intend to address 5 questions in this talk. As I start this presentation, I will go very slow, and then in the middle I will pick up speed because there's a lot of work, and then I will slow down in the end because that kind of gives you the key message.
Like workout in the gym.
Sorry?
It's like workout in the gym.
First the warm-up and then sprint, and then we will cool down. I would consider myself to have accomplished what Nicola wanted me to do if you remember answers to 2 out of these 5 questions at the end of the lecture. So the first one is, what is information processing, and what is nanotechnology, and why materials modeling within Intel, and what is materials design, and then what are the challenges going forward, and how do we address them today, and what are the challenges. The one thing which is interesting is one of the challenges which I had put in, you will see it's in my second challenge, was the same thing that Professor Cohn also said yesterday after the solar movie. So, I think it seems that we are approximately in the same direction as far as the challenges go. So what is information processing? So information processing is the basis of every computer chip in every computer. The whole thing essentially has what is called a binary processing. So let me explain what the binary means. If any entity, any information processing entity is on the left-hand side, it means the switch is on. If it's on the right-hand side, it means it's off. And we know that quantum mechanically, you cannot have a single well with the entity on both sides distinctly. So the way you address the switch is to have a barrier in the middle where you can switch it on and off. So you lower the barrier and it switches off. Then you have the barrier, then it is switched on. I mean, this is just an example. And you can see how it is switched on and off with the barrier and the particle at different entities. Now, the blue colored ball that is shown doesn't have to be a particle. It could be an electronic charge, it could be a spin, it could be any entity which carries information. So this is the basis of every computer, and you have billions such switches are acting in some sort of an architecture to give you the whole computer processing. Okay? So the entire computers are essentially a sum total of this binary switch which communicate with other binary switches put together in circuits and architectures. And the state variable determines what kind of a switch you have. You could have a molecular switch, you could have an electronic switch, you could have a spin switch, you could have ionic switches, and you could even have, the water switch, the gates that you use to get the water into the house and all that. All of them are distinctly switches, and all of them work under the same principles. But this is the basic of information processing where Intel, which is one of the leaders of making microprocessors, is involved in it. These switches are essentially operate by what is called Boolean logic, which is binary logic. And that's probably all that I'm going to talk about that. The important thing is, okay, where are the information technology components used? This is essentially a new way of looking at information technology. On the left-hand side, you have sensors, which are essentially displays you see in front of you. The information output, this essentially outputs the information to the user. So you have LCDs, organic LEDs, and plasma displays, and so on. In the middle, you have the output channel. So you have a user interface and an output channel, which could be a photonic network or neuroelectronic or any of that. On the right-hand side is the information processing, which is the switching process. So these are the three components that essentially make an information technology device. Moving on to what is nanotechnology. Nanotechnology is defined as the research and technology development at the atomic and molecular or macromolecular levels in the length scale of 1 to 100 nanometers. You should be able to process things under 100 nanometers. That's the strict definition of nanotechnology. Now, I put in here essentially different things which have different characteristic dimensions. You can see the small molecule is 1 nanometer or below. And then you have virus, several tens of nanometers. And 100 nanometer and above is when you have the bacterium come in. And most of the nanotechnology is in that domain on the left-hand side. So that is where we are essentially making the switches. And then you have bigger and bigger dimensions. Now, a better definition, which I think is a very prophetic definition, was a 1959 definition by Richard Feynman, in which essentially he gave a lecture called "There is a Room at the Bottom." So if you get a chance, read up that. There he anticipated what this nanotechnology is in 1959. And so, that is very prophetic. So the entire information technology operated in what is called Moore's Law. So the Moore's Law was something that Gordon Moore, one of the co-founders of Intel, observed in 1967, that if you were to plot it on a log scale, this is a semi-log scale. On the y-axis, you have the number of transistors on a single die on a given area. On the x-axis is the time. So Moore observed, based on 5 data points, that this is essentially almost a linear curve, that the number of transistors are doubling every 18 to 24 months. So he said that this will continue into the future. Now, if you were to take a sociological viewpoint of this is one of the exponential laws which has essentially completely revolutionized what humans can do. And this was essentially observed in 1967. And I put the reference in from 1965 paper. Now, if you were to fast forward into 2008, this is how the law has come out. These are real products which have come the last 42 years now. If you look into 2009, you essentially see that there are microprocessors following the Moore's Law. There are memory devices following the Moore's Law as well. So this law has essentially held true for about 42 years now. Okay. And this means every 2 years you get for the same price a newer computer. So this is essentially one of the reasons which causes deflation in the economy as well as we move along. So why materials modeling within information technology? That's the next question. So the material revolution is something which has essentially reborn in the past 4 years, actually 4 to 5 years. What I took one of the quotes from an Intel senior fellow. He essentially, if you look at the microprocessor, this was mainly device scaling. And he essentially made a comment that it is the new materials and structures which are going to get us newer and newer devices, not just device alone. You need materials as well. Now here, I essentially have, I don't have a pointer, but I use the pencil here. If this is not clear, I apologize. This is essentially an analyst firm which has looked at what are the 3 major pillars that is going to give technology. And they have process technology on the left-hand side, materials technology in the middle, and device design, transistor design on the third. So one of the pillars is essentially materials. And if you look into the right-hand side, I have drawn a periodic table and essentially shown you that it is not the number of elements that's a problem. What I have is a phase diagram between aluminum and copper. So even if you include 2 different elements, you end up with very complex thermodynamics in terms of understanding what the materials interact or how they interact. So the technology challenges, now fast forwarding. The first thing was what is called a Damascene process. This happened in the late 90s, early 2000, when copper was introduced into the technology. All the metal lines that were in a chip were aluminum before, and this got transferred to aluminum, from aluminum to copper. So that was the first new material. Then what happened was in early 2000s, what they did was they strained the transistor. They applied a mechanical stress which changed the band structure of silicon. So the silicon's mobility increased by a mechanical effect. So that was the second exploitation of a mechanical property of silicon. Then what is the tipping point in terms of the number of materials increasing was when they introduced what is called high K, high dielectric constant materials and metal gates. Transition metals were essentially used. And that means that you are introducing now materials much faster than before. The future is going to be even more complicated because all these materials we have introduced themselves may not be sufficient because we are running into some material intrinsic issues. And I have tried to picture it in a periodic table looking at some of the things we did in Intel. In the 80s, you essentially had micron scale dimensions. You had silicon as the primary substrate, aluminum interconnects, and 4 layers of metal. The transistor count was 2 million, and you were looking at 11 elements in the periodic table. You come into 2000, you are now scale the dimension 1,000 times smaller. Now you have introduced a plastic package from a ceramic package. Now you have introduced copper as an interconnect, and there are 9 to 10 layers. And the transistor count has become 2 billion. Now there are 2 billion transistors where you used to have 2 million 20 years back. In addition, the number of elements in the periodic table you are looking at are approximately 38 elements, which is about 3.5 times more. Now I tried to take a look at some of the materials we are looking for future technology, which is like about 70 elements we are looking at the periodic table now. And in terms of that, this is only 1/3 of the story. It is not the number of elements that the challenges are, but the very fact that the number of elements are now 70 in the periodic table essentially shows you the kind of things we have done. Now, why are these materials challenges? And I have tried to explain it in this very simple device, in this simple graph. On the left-hand side, this is where the transistor sits, and silicon is here. These are all metal interconnects which bring power and signal into the transistor. The transistor is about 10 nanometers, which is a future technology, and they are embedded in what is called a dielectric, which is a material with a lot of voids in them. So there are dimensions which are very small. And then the metal lines are embedded in further elements and complex oxides, which have its own structure. And then if you look at the resist which is used to pattern, they have dimensions as well. So if you look at it, there is a kind of a complexity coming in, because when you go below 20 to 30 nanometers, the grain boundaries of some of these materials are 20 nanometers. So the device itself is of the dimension of the material characteristic, which means the material and the device are starting to become almost of the same order of magnitude. So there is no real material at this point. Remember though, if you cannot have polycrystalline material, then you are really not having a material. So when the crystal dimension essentially comes to the same as the device dimension, then you are starting to get non-local effects come in. And that is one of the biggest problems that we face. So these are the number of simulations we did. I took a rough statistic. In 65 nanometer, I kind of normalized that if you looked at one particular material, in 45 nanometer, which is the next generation, we were looking at about 3 times as many. And when we came to 32, it was approximately 3 times. In 22, there are 5 times as many materials we are looking at. And in 15, where our current focus in materials modeling is, we are looking at about 6 times. Remember though, if you look at the periodic table, we are only looking at 2 times more elements, but the number of materials we are looking at is 6 times more. That's because there are a combination of elements which essentially constitute the material. And the problem is here, I have tried to capture this in a snapshot. The number of materials and their combinations, the interface modulates almost all the electronic properties we see. And then the combinations of these materials are limited because you have to integrate them all into a same particular chip. And you have smaller concentration of other materials of parts per billion type of defects, which you deliberately engineer in. And I mean, most of you know ab initio is probably not sufficient to be able to simulate parts per million defects. Now, what are the complexity in materials? On the left-hand side, I mean, when you go from left to right, the complexity increases. These are the kind of things we look at. Mechanical properties, the dielectric constants, and chemical stability are more straightforward. You can essentially try to be doing them with ab initio. When you get to the second box, you are starting to look at secondary properties. By secondary properties, you are looking at density of states, work function, and interface animation. So you are now one level removed from bulk material properties. When you go to the right-hand side, which is where actually the Intel is interested in, Intel's process engineers are interested in this side. You essentially have topography of structures. You look at contact resistance and Schottky barriers because you have semiconductors, metals, insulators, all kind of interfaces with each other. You have the IV characteristics, and then you have topology of the devices. The topology of the device, for that I have an example here. This is essentially a carbon nanotube on a substrate, on a contact. This topology of this nanotube is very important because that is what gives it its high conductivity. So both the topology and topography are factors of these materials that you wouldn't see before, which you would not have seen in bulk materials. The importance of materials has not just been seen at Intel. There is an international working group which looks at technology roadmap for semiconductors. And this is one of their diagrams which I took. If you look at it, it used to be, this diagram captures everything that they see are the challenges going into the future. The state variables, which used to be just electronic charge before, now has expanded to have molecular state, strongly correlated electronic state, and spin orientation, etc. Materials have found its own distinct position in the middle because what material you choose will influence how to optimize the state variable that is used in switching. Then the device is built up of materials, and the devices are essentially put together in an architecture, and that's what you have at the top. So you can see that the hierarchy is a lot more complex than anything that has been done, and materials is right in the middle of this as well. And if you go down or go up, you see the material properties modulate which kind of device you need to go up with. So now, going to the third question, what is materials design? So the materials design, this is something I took from NSF, but it kind of tells you what this is. I mean, this is a very good definition, which is why I just kept the same definition. Given a desired macroscopic property, how do we design from first principles a molecule or material that essentially possesses that property? So it's the inverse problem. If you look at everything we did in the class, we kind of take a material and then we go and try to estimate the property of it. But what is more relevant where I work is they know what property they want, what value it should have, what material should go into it. That is the question that constitutes material design. And then you have to go and make these materials. That's where the synthesis comes in. So I have given an example of something we did in Intel here. This is a very simple example. On the top, what we did was we used essentially quantum chemistry modeling. On the right-hand side, you see the substrate. On the left-hand side, you see a gas precursor, organic precursor, that was essentially used to grow a certain film. This is a material design in the sense we designed a precursor that will have a certain specific growth on the substrate. So this was an inverse problem. On the bottom is a polymer design. We essentially took a cross-linker and a backbone and put together a polymer which has essentially specific mechanical and thermal properties. So both of these were solved as inverse problems. Okay. So what are the challenges? And this is essentially a key part that I want to show. If one were to have a wish list of how materials modeling could be used, this would be the intent. You are able to synthesize what you need, put it on a substrate that we saw. So both of these are part of synthesis. Then you essentially put together a structure which has a certain desired property. So that's a very important thing. And the structures could be of any topology. It could be planar topology or it could be non-planar topology. And then you measure the property, which is essentially where the metrology comes in, and you essentially come back with the measurement of the property. What I am showing there is the resistivity of copper as you reduce the dimensions, and as you can see, this is all predicted from first principles modeling, and you can actually see that the resistivity goes up very high. So this is kind of giving you and compare the data, by the way, the points of data. And it kind of shows you what would be a wish list. So the four major components of modeling are synthesis, structure, composition, probe interactions, and properties. These four constitutes what I consider the key challenges in materials modeling. Now the nanotechnology that I mentioned to you below 100 nanometers has basically two paradoxes. People would argue intuitively that if I reduce the dimensions, I have fewer atoms. I should be able to simulate them in first principles. So why can't I do that? But it does have these two paradoxes. The size is in nano dimensions, but interfaces to bulk ratio is much higher than 1. So this means that interfaces modulate all the behavior that we see, not bulk materials. Then in addition, you have non-local effects. Since there are multiple interfaces, you have effect from materials farther away affecting them. And then, in addition, you have new structures which are chemically different that are integrated together. So you have cross interactions between materials as well. That's one paradox. The second paradox is metrology is unable to characterize these properties because they are so small and the measurement is for generally bulk materials and bigger structures. As a result, you use modeling to deconvolve measurement. So these two is why even if you are in smaller dimensions in nanotechnology, below 100 nanometers, you can't be predictive. Because you can't even measure, and even if you are predictive, then the point of validation is difficult. And I have tried to put together, when I first told Nicole I had 10 challenges, then when I put them together, they ended up with 14. So that's why I put 10 plus challenges here. So let me go quickly over this list, and then The ones marked in yellow, I go in a little bit more detail to kind of give you an idea of how we have solved them. The first is bulk properties. So what is complicated about bulk? We have defects even in bulk materials which are parts per million, and we want to be able to measure the electronic properties, because we have found out that parts per million defects are essentially modulating properties. Interface structures and potentials you need for interfaces of materials. Then the nanostructures where topology and topography both essentially influence that. I went through that. You need band gap, so excited states is an important challenge. Then you have temperature dependence, which comes under equilibrium thermodynamics. Then you have non-equilibrium, which is essentially transport, because the IV characteristics I talked about. You need to be able to predict properties in terms of external fields. And then correlation, where you have phonon-electron correlation, photon-electron correlations, and multi-scale correlations. That is a larger scale, how does it affect the smaller scale, and vice versa. Remember, when I say larger scale, I'm talking about 100 plus nanometers versus 100 minus nanometers. Then synthesis is another challenge, because you need to be able to make these materials with properties. On 10 is there are new classes of properties that are very important called emergence, where you have phase change agglomeration happening in materials as well. Then 11 is time dependent, coefficient of thermal expansion, glass transition temperatures, and many more, which are time dependent. And then the thing is, even if you have a lot of computers, the algorithms are not scalable and they are very memory intensive. So these are the other challenges we have. And then the software. We generally have software which are in bins and they don't necessarily talk to each other. Since we use a combination of tools, it is very hard for us to be linking things from one tool to the other. So this is actually a challenge as well. And finally, the measurement, which I will not go into it. With that said, let me kind of quickly go through a couple of examples in bulk and interfaces. I will rush through the next few sections, but I'm willing to stay back and answer questions if you have either today or sometime later this week. The first one we did was estimation of dielectric constant. What you see are two materials that we essentially designed in which we wanted a certain specific properties. So we were looking for low dielectric constant. We wanted to reduce the capacitance of the material, so we were looking for low dielectric constant. The way we went about doing this is for metrology we use NMR, because that gives you the nuclear information and chemical composition. Then the modeling was essentially a combination of properties, a combination of tools and techniques were used. The bulk material essentially, we were looking at surface materials because these are small structures. Cluster molecules were put together to look at the properties as well, in addition to surface structures. And a composite theory to be able to correlate it with the experiment. What I show on the right-hand side is the way you essentially get the properties is you take a cluster and put void at specific locations in the material. So you have to take out the molecules that have properties which are non-optimal and put materials in molecules which have optimal properties. So here's an example. We took SiO2, which is the most commonly used dielectric, and the SiO2 network has essentially oxygen, silicon bonds to a valency of 4 with oxygen. And each of the oxygen atom is replaced by a methyl radical. So what you are seeing here is what if you were to replace one by one. And what you see is the sum total of these. Quaternary stands for all 4 are oxygen. Tertiary is 1 oxygen replaced by methyl. Dual is 2 of them. This is binary. And then mono is just 1. So there's only 1 link with oxygen when you come into mono. So the whole lattice is broken and you have essentially inserted functionalized molecules into the dielectric. So here,
how can the materials stay together? I mean, if you substitute all the oxygen with a methyl group, that would become A molecular crystal, right? A very
Right.
soft one.
Right. So it is exactly. So the problem was it becomes so soft that the material breaks. So what in such a case, what we had to do was we had to have the encapsulation so that the material's mechanical integrity is maintained by other materials around it. So this material, you are right. I mean, two things happen. I think if you think about it, you will see that quickly. The first one, you said the material becomes very soft. It could collapse mechanically. That's one. The second thing is it becomes very hydrophobic, which is a good thing because we use cleaning solutions and essentially you don't want water going into these pores and sticking in. So it helped in one and it became worse in the other.
So you need the matrix to keep all
That's
this
right.
together?
That's right. That's right. And we even did something even more complicated. This chip is packaged into a bigger package. So what we did is we put in materials which essentially like pillars held the stress upwards of this material. So the integration, a material problem was solved by an integration solution. You essentially solve the rest of the things to be much more harder, and that would absorb the stress so that this material itself will see lower stress. That's the way. And this was essentially done in 2001. Since 2001, Intel has been putting these kind of materials into the chip because they reduce the RC delay. When the electrical switching in comes in, you won't have very low capacitance in this material. That's why we reduce the dielectric constant. In the front end, we have to increase the dielectric constant. That's a different effect. The second thing is interface property. These are copper lines which are embedded in materials. But however, this copper is surrounded by some other material because otherwise copper diffuses into the background substrate. So our intent here was to essentially look at copper adhesion with X-stop and barrier layer. This was a very big problem when copper was introduced, and I want to show you the problem we had. This is essentially agglomeration of copper on a particular material, and you can essentially see it doesn't wet. But this material has certain very nice properties that you need it for, but however, copper and that material are not compatible. So here our intent was to be essentially be able to predict this interface adhesion and try to see how we could solve it. And this is very straightforward for our calculations here. What we did was we put a stack, which is copper, and then we put in the material that we wanted to look at the adhesion. And we estimated the energy of adhesion of these different materials in there. Now, one subtle point here. The real copper is not single crystalline, but we looked at single crystalline materials because the polycrystalline is a very hard problem to solve with ab initio. So, but the single crystalline material predictions essentially turned out to be pretty good. What I show here is copper adhering onto the substrate, and this is the copper atoms. And we looked at both LDA and GGA, and you can essentially see we minimized the energy and took the adhesion energy out of it. Very straightforward calculations. So what did we do with it? These were all the materials we looked at it. The surface affinity going from the lowest on the left to the highest on the right. And so we predicted that you don't want tantalum, you would like to stay around this side. You want to be in tantalum because this is surface affinity. You want to stay away from the left-hand side. And what you have are the actual measurements. And you can see that this is essentially providing much better adhesion on the right-hand side than left-hand side. So the modeling, remember though, in a setting like Intel, it's not enough if you predict. You need to be able to have it validated somehow so that they could essentially use the material before they start shipping it. Intel ships over 100 million chips every year. So you can imagine if any of the chips start delaminating in copper lines, I mean, you are talking about billions of dollars of loss. So but before it essentially goes into the technology, we have to have this validation, which is what makes it much more challenging. in use of ab initio techniques. So the next is topology and non-equilibrium. What is non-equilibrium means different things, but I just wanted to show you what we mean here. Non-equilibrium are essentially open systems. That's what I'm talking about. Open systems, essentially you look at transport here, and the thing that we specifically looked at here is metallic CNT on a metal substrate. As a substitute for copper, can we essentially try to look at metallic CNTs, carbon nanotubes for copper? So the technique here is a little bit more complicated. We essentially do the DFT calculations. You have a nanowire connecting two metallic reservoirs. These two metals, which are contacts, are the same. So after you do the DFT, you essentially take what are called self-energies and put it into a non-equilibrium transport equation. And then you try to get the transmittance out of it. And that's what this particular methodology used. So here the point is, I just wanted to show you palladium was one of the metals on which the carbon nanotube was grown. And we wanted to, and people were seeing difference between different metals and different sizes of carbon nanotube. The key thing I wanted to show, this ties in with what Professor Stephen Louis showed actually yesterday. What I'm showing on the x-axis is the diameter and the conductance. What you see here are actually data. This is the first data coming from Hongji Dai's group in Stanford. These are our predictions. As most of you with DFT know, that DFT always over-predicts conductance. There are a couple of reasons for it. And Professor Stephen Louis explained it nicely. But the key point, which was more important to us, is we caught this trend very nicely. We actually found out that when you reduce this, your conductance essentially comes down. And what was the reason for it? And the reason for it essentially can be looked on from three different components. This is a metal here, and this is the carbon nanotube going to the other side to a different contact. There is the metal to CNT interaction, the so-called contact resistance. Then the metal chemically interacts with the CNT where it contacts. So this part of the CNT essentially deforms. While the center part of the CNT does not deform, this deformity quickly gets back to normalcy. So you have an interaction between the deformed CNT and the straight CNT, and then transmittance through this, and so on again. So these are the three different attributes to conductance through a CNT, in addition to phonon scattering and other things that go on. So the first thing we did was we essentially simulated the barrier effects, and we found out that the tunneling barrier becomes more negative as CNT diameter decreases. So this will not explain it. So what this means is you actually have no barrier when the CNT becomes very small. So you do not necessarily have this contributing to the reduced conductance for smaller diameters. So that's the first study we did. The second one is the region I said where the CNT on top of the metal itself is deformed. And here if you look at it, these are, sorry about the fonts haven't come out nicely here. But we are looking at armchair and zigzag CNTs here. And these are the diameter dependence. The key point I wanted to say here is the conductance drop depends on the type of metal, and the conductance increases with CNT diameter. So this is the key factor that was contributing to reduced conductance with smaller diameter. The deformed region was essentially leading to a reduced conductance for smaller CNTs. And I have more information, but I will kind of go through this. The next thing is synthesis. Here I'm showing the metal gate high K. This was essentially deposited by using what is called an atomic layer deposition process. Single layer at a time, you essentially grow it. Single atomic layer at a time. So here, they were looking for how to optimize it, and I will rush through this, but if you do have questions, I can always stop and talk to you about it. So here we are looking at typically a CVD process and an atomic layer process. A CVD process means put all the gases in at the same time. Atomic layer means you put one gas at a time. It has a self-limiting growth. Then you put the other gas and it grows on top of it, so you control the growth. That's what the atomic layer deposition is. And some of the key things is this is aluminum oxide is a high K dielectric. And the reason we have to use modeling is for new gases and new precursors, they did not know a lot of the properties. And some of them were toxic that you could not do experiments in detailed manner. Well, in simulations, of course, we have the luxury of not getting the toxicity part of it. And then it could guide the experiments for ALD optimization. But the problem in ALD is not just the rate kinetics alone. You also need to be able to look at these multiple time scales. You have the gas flow into the growth regime. And again, I will not go into the detail. There were 3 parts to this modeling: gas phase calculations, surface structure calculations, and then essentially try to put the kinetics on top of the surface. These are essentially DFT simulations looking at different energetics here, and then you put together the transition state and estimated the barrier height for this particular system. This was done using Gaussian, in case you are wondering. And this essentially shows the whole reaction pathway constructed going through the transition barrier and then coming into a product. And these are very detailed computations, but I will not go into it. The summary of this is we put together the overall reaction of aluminum oxide, and at the end of it we got the kinetics. Now what? We got the kinetics, but remember, kinetics is only one part of it. We need to grow the film. So then we go to the next step, which is the reactor modeling, where we took this kinetics and then we essentially put it into a flow reactor model. And what you get out of here is on the left-hand side is essentially the experimental measurements. It's all the same scale actually. We have drawn it to the same scale. The time, x-axis is the time, y-axis is the aluminum oxide thickness. If you look at that, you essentially see the graphs are more or less nearly identical in terms of thickness. The right-hand side plot is essentially the growth rate. So you essentially see the stepped growth because you are controlling it one layer at a time. So this prediction is what is more relevant from a technology perspective because they know how to optimize the reactor conditions and the chemistry with it. So that's the synthesis part.
177 sees the temperature?
Correct. Celsius.
But most of these devices should operate at room temperature and slightly above and below. Is there any reason?
You are talking about transistors, right?
Yes, whatever device you
The transistors are approximately on the order of 100 degrees Celsius when a transistor operates. Right? This is when you grow the film and you haven't formed a transistor yet. Remember, this is the dielectric. If you look at the growth, you have silicon, then a channel where the switching takes place. On top of the switching, you have what is called the gate because this is MOSFETs. So you essentially have a dielectric. On top of that, a metal gate. So you are still in the process of making the device. The budget for the highest temperature in processing is 400 degrees Celsius. Nothing can go above 400 degrees Celsius. Below 400, it's okay. We have tricks. We use higher temperatures. Process engineers use higher temperatures, but they use them for microseconds. So you have pulsed heating, laser heating. So people use the tricks. As long as you don't have 400 degrees, you don't ruin the device characteristics. Did that answer my question? So the next is algorithm and scalability, and this is a very simple example I try to put together. Lot of the things that we as I think Nicola showed it today. At least I saw in today's one of the lectures I saw today. The timing. So what I have drawn here on the x-axis is the time in seconds, that realistic time, realistic process time that I want to simulate it. On the y-axis is the flops for something like an atomic system, molecular dynamics type simulations, what it will take to do the flops. We are currently here on the order of something below nanoseconds that we can simulate. A lot of the processes that the technology needs and they measure is of the order of milliseconds to 24 hours. Now you could ask me, why do you need 24 hours? A lot of reliability testing that they do the devices are done 24 hours because that accelerates the real conditions that we as users put the chips through. So a lot of material properties they need to measure time-dependent properties of the order of 24 hours or more. I mean, it's of the order of 1 day. So if you look at it, if you were to look at the time scale that you would need to be able to simulate it all based on just atomic model, you will essentially end up with some very large time requirement. Now, I'm not saying this is the way to do it, but this is what if I could get to do it. So one of the questions that I was asked is, before I started this exercise, some senior high computing division at Intel, they came and asked me, how much computing power do you need in order to do your job right? That was a question that was asked of me. So we essentially went and did an analysis and found out that they were trying to make a case for petascale. And we said, petascale computing we could use of the order of 10 to the power 15, but we need more than that. Right? Just for your information, if you look at overall in the technology area, we are the second biggest consumers of computing cycle all over Intel. Materials related activities, because it uses almost every extra computing cycle in order to be doing the simulations that I showed. Now that's one. If you look at the length scale, the number of atoms needed, this is again very back of the envelope calculation, but this makes a point I want to make. We are here, which is essentially the green rectangle. This is atomic scale. So what we can do with atomic problems if we are it's of the order of million. You can essentially go up to billion with very large scale, but it's still of the order of here. We need to be able to go up to 10 to the power 12 if you were to look at the whole nanostructure you want to simulate.
I don't understand this figure. What do the different lines actually mean?
Okay,
colors?
Let me explain. This is essentially, if you started with this kind of a flops, the y-axis is flops, what it would take to solve a given problem, the floating point instructions per second. The x-axis is the number of atoms for different techniques. That if I were to use a given technique to solve a given size problem. I have looked at n scaling, n squared scaling, and n cubed scaling.
Atomic or what is it?
Sorry? Atomic is essentially molecular dynamics, classical. Classical. I am assuming that I have incredibly good potentials. And then if I don't use ab initio at all, so this question gets asked of me, why can't you use classical MD? And so even if you start with that, you need of the order of petascale computing, assuming you have very good potentials for all the chemistry that I showed. Even if I go with an order of n scaling in DFT, in order to get to this particular problem, now why do I have it at 10 to the power 12? 10 to the power 12 is we looked at all the properties, all the structure, microstructure domains and all that. And if we were to have a wish list, we would like to solve 10 to the power 12 atoms. Now, remember though, we are here. So even if we have this, we can still solve the problems, but with a lot of difficulty by putting together things, extrapolating and putting semi-empirical things and so on. So the intent is, if you want to be all predictive, all ab initio, order of n scaling of DFT, you are already on the order of, this is what is called the exascale computing, 10 to the power 18. Even that will not be sufficient in order to hit the 10 to the power 12 atoms that we would like to simulate. So the one point I wanted to make is that you need major breakthroughs in the algorithm level itself to be able to simulate between here and here. the current scaling doesn't get us there. Because if you wait for exascale computing is at least 5 years out. You miss 2 generations of technology in which you could predict things if you wait to get a faster computer. So the intent is that if there are some major breakthroughs that may be needed in the techniques, both in the ab initio and even in the classical NP. Then the next one is software. This is one of the things which I think, Nicholas is very much aware of some of this, which whenever I have had a chance to talk to him about. Lot of the things we use in terms of software are third party, in the sense it's developed elsewhere. We don't sit and develop software with Intel. We use what exists out there, like Quantum Espresso or VASP or Gaussian or any of the tools that you can think of, or Siesta and all kind of combinations. But each of these tools, each of these capabilities are done by a different tool. It's not the same tool that does all this. Structure creation itself is a very complex area, as you can imagine. Electron dynamics is different, phonon dynamics is different, atomic diffusion is different. We cannot essentially have the tools talk to each other. There's tremendous time wasted in trying to take information from one tool, transform it, put it into another particular tool to be able to do what we want. So part of this is to have, the intent here is to say that it would be good to have an open materials, open platform where we could do these simulations. And what is an open platform? I kind of went into somewhere on the website, and this essentially says that the open platform doesn't mean open source. You are not opening up all the source, but you are essentially having the interfaces talk to each other in an open sort of way. And that's essentially the intent of this as a challenge. I put together some of the requirements. They need coupling between tools, database accesses, and all of that. But I will not go into the detail, but you can essentially get the picture of what I just said. So where are we today? I think that full quantum simulations can be done for smaller atoms, smaller systems of the order of 1,000 atoms. That comes to about 3 nanometer cubed. Semi-empirical modeling can go to millions of atoms, but need very heavy characterization. The potentials are a big problem, actually. I'm talking about both the classical potentials, pseudo-potentials, and even semi-empirical potentials. Now, the empirical and mesoscopic atoms can go to very large scales, or continuum scales, and so on. But they all need enormous characterization of properties. So you have no way of predicting the properties for smaller nanostructures without any of the top two. And so capabilities and computing infrastructure are issues. And so the summary, coming down to the last 2 slides, the summary of challenges are thin films, the interfaces dominate over bulk, nanostructures have topography and multiple interfaces, materials have combinatorial in nature, and then you have software and models are not scalable. Some of them are unreliable and limited to very well-known systems. And computing is, the Intel's general computing environment is very heterogeneous network. So it's very hard to be able to use that. And kind of I want to end it with this particular slide. So we are actually back to the future, if you think about it. The era of material science now and technology, which was in the early 20th century, when metallurgy started coming in, is now reborn as nanomaterials now because of these nano dimensions. And I wanted to show a quote from Paul Dirac in 1930 when he said, the Schrodinger equation can solve any problem you want. So it becomes desirable that approximate practical methods, he called them, of applying quantum mechanics should be developed, which can lead to explanation of main features of complex systems without too much computation. So that was his prediction in 1930. But if you fast forward to 1998, the Nobel Committee thought that the John Pople and Walter Cohn's awards essentially says the numerical technique, it's not as trivial as what Dirac had postulated. And I just wanted to put the quote where they used that the theoretical studies of the properties of the molecules, they were involved in developing methods. The same thing that Dirac said was not that complicated. And the point I wanted to make was the era of nanomaterials is very different than the bulk materials we are used to. And that is where all the fun and challenges and research. That's all.
Thanks for this illuminating lecture on what expects us for the next 10 years or so. Are there questions? Andrea?
You mentioned calculation of phonon in the interface of Doppler and in the interface of Doppler and the normal area. But how do you use the phonon?
How do I use the phone?
Yeah, you just mentioned phonon. But
Right. So we look at we stack the two materials, and then you leave air, the vacuum at the top, so you have an extended structure. You break the symmetry, and then essentially simulate it like now a complete structure.
So it's left
Correct. Slab with broken symmetries.
and to understand what?
To look at the adhesion. So, two things, right? You essentially need to be able to estimate the adhesion as a function of temperature as well. So what I showed you was the energy, the surface energy, right? The energy of this. What we do is we essentially start with two surfaces, and we kind of bring them closer, and essentially look at the energy where the minimum energy is, and then essentially use that to estimate whether one surface energy is lower than the other.
Which materials were they?
They were things like tantalum, titanium nitride, tantalum nitride.
Versus, so the two interfaces.
The copper on one side and titanium nitride or tantalum nitride on the other. So you essentially bring them together, keep looking at the energy. It's a very cumbersome calculation. I mean, it's very manually done. But the intent of that was to look at the energy of interaction between these two surfaces.
What is the largest system size till today people are able to simulate?
So it depends what technique you ask about.
Whatever be the technique.
So
Say independent of
atom.
Yes.
I have seen multi-billion atom simulations. Multi-billion atom simulations, but by using semi-classical MD. If you, I mean, Stefano can
You
probably.
have seen and used or
I
judged it to be meaningful, or was it just
that's a good question. The billion atom simulations, multi-billion atom simulations, we haven't done that too much because you need enormous computing, and then you can do it only for simple systems of which there is no interest or utility for the properties. So we don't attempt that. What we try to do is we try to use smaller systems and try to look at multiple combinations of materials and then extrapolate it to macroscopic systems. For example, void nucleation, if you were to look at it, we would look at vacancy formation and then essentially use the vacancy formation and try to see if we can predict what would be the threshold hydrostatic stress in which voids nucleate. So those kind of things we have done of the order of 1,000 atoms.